I'm Kevin Short. I'm a professor of mathematics in the Department of Mathematics and Statistics here at UNH, and I'm currently in my 25th year here. So for about the past 20 years or so, I've been working in the combination of signal processing and chaotic analysis, which is a type of nonlinear behavior that has rarely been controlled for practical applications. And in this case, we discovered that chaotic systems, which have a lot of properties of randomness, can actually be controlled. And some of the early applications we worked on were things where we were doing music compression. We created a music synthesizer, things like that. But we later discovered that these systems, which would normally sort of wander off in a somewhat random way, you could actually couple two of them together and they would stabilize each other. And the cool thing about that was once they were stabilized, they would retain their sort of entangled state. And we realized that we could use that to store information. And once you can store information, you can start thinking about building things like computers out of it. One of the really popular things these days is this idea of quantum computing. And the difficulty of quantum computing is that they're dealing with systems that they really believe are in a somewhat random state, or at least it's not deterministic and they can't know the state of the system. So they're constantly trying to figure out ways to tweak it and find methods to bring it under control. Because a quantum computer doesn't really work for you if it gives you a wrong answer some reasonable large percentage of the time. So these chaotic systems have very similar properties, but they are controlled, and we've found this control mechanism so that even though they are generating a wide range of different behaviors, once they entangle, they lock in a particular state, and that particular state has information like you would store on a computer. We also went a little bit further and showed that we could actually build something like a NAND gate out of it and other kind of computer logic gates. And so it seems natural that you could extend this further and build entire computers out of this type of technology. People are always talking about how rapidly quantum computing is going to appear, but the horizon always moves. And so this could be one of those things where we talk about it for 50 years before anyone can really harness it and get it under control. Whereas with our technology using chaotic entanglement and the idea of chaotic computing is probably a bit more straightforward. The main differentiator is the ability to control the systems in a known way, rather than try to estimate the state of the system in a statistical manner, which is what they would do with quantum computing. We actually have systems that will synchronize with each other and into known states. So you can simulate it, you can then compare your simulation with what your circuit implementation and make sure that everything syncs up perfectly. And that means that you can do much more rapid development as they've done with circuit-based technologies in the past. We applied for a patent a couple of years back, and that patent has recently been issued. So the technology is in place, but we need to take it to the next step.